Hi everyone, good morning.
Good morning, sir.
Morning. All right. I hope my screen is visible to every one of you.
Yes, sir.
Okay, great. So guys, last class I think we had a quick theory session on regression analysis, right? Where we learned why do we need regression, when does a regression work? We learned concepts with respect to, you know, estimating the parameters using OLS method, line of best fit, R square, adjusted R square,
So,
the concept of, yeah.
I think your screen is freezed. Like your video is paused and your screen is also freezed.
Okay. I think it might be a Chrome issue. Just give me a minute.
Interesting. Now it's okay.
Yeah, now it's back to normal, I think. Yeah.
Yes, sir. Yes.
Okay, great. All right. So guys, again, we can spend the first 15 to 20 minutes of the lecture discussing if you have any concerns or questions on what did we learn last class. Because today we are, trying to understand or learn, an extension to what we did last class in R. So if there's any concept or if there is anything you want me to revise or you have a doubt upon, you can, just feel free to let me know. Yeah, Riya, Kaustav, Bhavani, Ali, if you guys have anything to discuss before we start for the day. Okay, thanks, Ali.
So like
Mhm.
we discuss about the adjusted R square again.
Correct. We discussed about adjusted R square at the very last concept in our last lecture. Correct.
Mm.
You want me to revise that again?
Just not in detail, just
Mm-hmm.
overview kind of.
Mm-hmm. Fair, fair. Chalo. So since we have R today, what I will do, right? I will directly, kind of um demonstrate it with numbers only, so that a lot of things would be quite clear to you guys. Okay. Is my screen visible to everyone?
Yes, sir.
Yes, sir.
All right, great. So guys, last class we learned something called as R square, right? And we learned that this is nothing but helping me as an accuracy metric, correct? It basically helps me understand the goodness of fit of the model, right? Now, when we discussed R square, we also learned that R square has a problem, right? So we learned R square has a problem, and the problem is that it is a non-decreasing function of xis. Now, what do I mean by that? When I write non-decreasing function of xis, non-decreasing function of xis, I mean that even if I keep on adding garbage xis, now when I say the term garbage, I mean x is not helping me predict y, correct? So if it is not helping me predict y or helping me predict y in a more accurate manner, then technically this x should be removed from the model because I don't want unnecessary complexity in the model, right? So now the problem statement comes that, okay, R2 does not help me with that. Then what should I, kind of look at? This is where adjusted R square came into the game, helping me say that if you add a garbage variable in a model, which is not helping you explain substantial value in Y, then R square would reduce, right? So a main drawback of R square that it would never decrease kind of got catered by adjusted R square, where it says that I can reduce if you add, you know, uh, X that is not good enough, let's say. Everyone good to go till here? Guys, yes, no.
So can you frame it in a different way?
Sorry, can I?
Like, can you frame it in a different way?
What should I frame it in a different way?
The last adjusted answer.
Huh. So see, R square, I'll put it very simply, right? R square is nothing but an accuracy metric. It basically tells me how accurate my model is. So when I say 90%, I'm saying 90% is the accuracy. When I say 75%, 75% is the accuracy. Are we all clear with R square?
Yes, sir.
Yes,
Okay.
sir.
Now, when I say R square, there is also a problem with it. The problem is that if I add xi's that are not predictive of y, R square does not come and tell me that, hey, Tanish, this is a garbage variable, don't add it inside the model, right? How would you evaluate if something is good or bad? If something improves the accuracy, you would say it is good, right? So R square has the problem that it can never reduce, right? So even if I add 100 of garbage xis in the model, even if I add 100 of variables that is not helping me predict y, R square is not coming and telling me, hey, that there's a problem in the model. You are adding variables that are kind of garbage. That is not helping you improve your model substantially. This is something what I would this is something what I would like to know as a modeler, because I hope you would appreciate if I add 10 xis, right? Versus if I add 2 xis. The level of complexity you are creating or the level of complexity you add in the model, the amount of time it takes to train the model will differ for these 2 versus 10 xis, right? Is the language still here in a very simpler format?
Yes, sir. So we are reducing exercise in
That
adjusted
is,
answer.
this adjusted R squared will give more parsimonious model.
Correct. So Ria, my objective is not to reduce exercise. My objective is to reduce exercise that are not helping me predict y. See, if you have 100 exercise and all 100 exercise are helping you predict y, then I am not bothered to keep 100 exercise. Don't keep that mentality that I'm trying to reduce x. I'm not trying to reduce x. I am trying to reduce x given it is not helping me predict y.
Yes, sir. Yeah.
Right? So don't keep it in that fashion that maybe I just need to have lesser exercise. Obviously, if you keep lesser exercise, the accuracy would also reduce. Yeah, Ali.
Yeah, sir. Based on your explanation, R square is also only important when you have multiple linear regression, not only.
Adjusted R square, right?
Yes, sir.
Yes. So whenever you switch to multiple linear regression, adjusted R square is the metric what you would be very keen to look at.
Thank you.
Yeah. Okay. So now coming to this problem or further extending to this problem, R square is not helping me with that. That is where adjusted R square now comes. Adjusted R square now tells that if you add something garbage in the model, right, that is not helping you predict y. Basically, in that scenario, adjusted R square would reduce. By the very definition, when it reduces, it is now helping me tell that, okay, this is something not adding substantial value to the model. Please don't keep it inside the model. Ria, does that help?
Yes, so we are reducing the garbage variables.
Yes. You are trying to reduce or eliminate the garbage variables from the model. You are not interested in reducing xis that are helping you predict y. So even if you have 1,000 regressors in the model, even if you have 1,000 independent variables in the model, even if you have 1,000 xis in the model, if each one of them is helping me predict y, if each one of them is contributing towards predicting y, then I'm not concerned about them. I would be happy to retain all of them. The problem statement is when someone is not contributing and is within the model. Guys, see if that makes sense. Okay, great. Great. So I will quickly just demonstrate you guys here, as to how, so I think we drew a chart last time. So I will just quickly help you visualize that relationship numerically in R, correct? So let's say I'm just adding a couple of garbage variables here. So when I say garbage variable means G1 stands for garbage variable number 1. Why do I say it as a garbage variable? Because, I'm just initiating some random values here. Right. So I'm saying that go to, continuous uniform distribution, generate 32 random values. Why 32? Because empty cars have 32 rows, hence 32 random values. From the range of negative 10,000 to positive 10,000. Again, it's completely random. You can kind of just select whatever you want. So let's say I'm creating 3 garbage variables, G1, G2, and G3. Okay, guys, do you appreciate and agree this is all these 3 are garbage variables because you have generated them, you have initialized them completely at random. It has nothing to do with if I have to predict mileage, right? If you remember in empty cars data set, you have a column called as mileage, right? So mileage would technically have nothing to do with respect to these 3 garbage variables what we have written down. Do you appreciate with that? Okay, great. So I'm just executing. If you remember, or I don't remember if I told you guys, how do you create a new column into any data frame? So you write the data frame name, you write dollar. If you remember, dollar was to extract a particular column. Since there is no particular column at the moment, I want to create G1. Hence, I write the variable name. It is whatever name you want to give, let's say. And then what you want to equate that column with. So I'm equating that column with, let's say, RUnif or some random values from continuous uniform distribution. And I'm creating 3 such columns. So if you see my empty cars data set, you will see the first variable name is MPG and the last variable name is carb. Now, when I keep on executing 1, 2, and 3, and again, when the view the data set, you will see G1, G2, and G3 all kind of having random values from continuous uniform with range of negative 10,000 to positive 10,000. Everyone, simple, good to go till here?
Yes, sir.
Okay, great. Now, what we will do is we will just create a regression model, right? So we will create. I haven't taught you guys exactly how do you create a regression model, so don't worry on the coding part. Just kind of focus on what I am trying to highlight here in the concept of R square and adjusted R square, right? So R square would give you obviously the R square value and adjusted R square would give you the adjusted R square value. So I'm just adding, let's say, a couple of variables here, weight plus cylinder, let's say. And let's say now I start adding the garbage variables. So again, don't get worried looking at the program. We haven't learned how to code all of these. And let's say I add the final variable G3 as well. Okay. All right, great. Let's try to see it now. So here I'm saying my mileage is dependent upon weight, right? So I'm trying to use my weight as a regressor here. So I have a 75% accuracy here for R square, and adjusted R square kind of comes to at 74.45. Now, when I also add cylinder to the model, what is your understanding? Should the accuracy of the model increase or should the accuracy of the model decrease?
Increase.
Yes, it should increase technically. Let's see if that's happening. Yes, so if you see now the accuracy improves from about 75-ish odd to about 82, 83% here. Guys, everyone makes sense? So if you see, since cylinder was adding a lot of value to the model, adjusted R square increased from about 74.5% to 82% approximately. Everyone, are we on the same page here?
Yes, sir.
Okay, great. Now let's start to add the garbage variables. G1, G1 plus G2 and G1 plus G3, right? So as per our theoretical understanding, if you guys remember, R square would never reduce, right? So despite adding a garbage variable inside the model, R square would tend or rather would tend to say me good things. Let's see if that's happening. So if you see, this was the R square from your earlier model. And the moment you added a garbage variable G1 here, you see there is a very marginal increase in the R square, right? It was 2274 at the back end. Here it is now 2463. Since you now know it is a garbage variable, look at adjusted R square. Adjusted R square earlier was 81.85. With this addition now, adjusted R square reduced from 81.8 to 81.2. So this is that information what adjusted R square tries to tell you, that the variable what you have added inside the model is not substantially able to help you predict Y than before. Hence, adjusted R square also tends to decrease, highlighting that the variable what you have added may be a potential garbage variable. And this is very clear at the moment because G1 was the variable what I myself created and added into the model, right? Let's also look at G2. So now there are two garbage variables entering the model. Let's see if we further reduce down the accuracy, right? So if you see here, R square kind of increased from 83 to 85%. Adjusted R square also kind of increased. Now this is possible because you only have 32 observations here. So the random sample what you have might be a little more inconsistent. Hence you see that number increasing. Let us take one more try over here. Or let me take another sample altogether for us to view. Right. So I'll just run the entire program again for us to view. So now if you see, it goes from 81.3 to 81.7. Okay, surprising that it is increasing. So we are getting a good set of bad samples. Let me just run it again to see if it's working. Yeah, I think this one should work. Okay. Let me just give it another try. Or let me maybe increase the sample size if that works. Okay, just let me do one thing. I will just, let's say, increase the sample size so that just give me a minute. I'll just increase the sample size. Let's say R bind empty cars to 4. Let's make it into 5 for that matter. Let's say into 5. Yeah. 1, 2, 3, 4. Probably now we should not encounter that. Let's go one by one again. Right. So till here, my adjusted R square is 82.8 and my R square is 83. Let's start to add the first garbage variable in the model. Yeah. So now if you see, adjusted R square kind of reduced. Correct. So it reduced from 82.8 to 82.7. Let's hope for G1 plus G2 as well. Okay, it kind of again increased. So again, I hope this is just a random sample, right? So it might be just a luck or a bad luck, you can say, where it has been increased. Let me also add G3.
These G1 and G2 might have a linear relationships also.
No, it will be random, right? It's all random. So
They may have some kind of a relationships. No.
Correct.
Because
No, the relationship would not be linear. It will be random only. It's all randomly generated data points here, right? So it will not be exactly in that fashion. Maybe I'll just reduce down the range to, I don't know. Let's see if that works. So ideally you should see a clear trend. I don't know why it's not happening at the moment. Let's see if I just remove empty cars, bind it again, 1, 2, 3. Yeah, I think we have that now. So I've just reduced the range of the random sample So now if you see with addition of one garbage variable, 82.8 to 82.7, with addition of another garbage variable G2, 82.7 further reduces to 82.6 approximately. And with addition of another variable G3, it further reduces to 82.5. So if you consistently see adjusted R square, it keeps on dropping. But if you see R square, it goes from 83.0 to 83.15 approximately, or 14 approximately. So R square never reduced, but adjusted R square did reduce to tell you the information that the variables what you're adding are kind of garbage variables. Guys, see if this helps you. So this was the exact theory what we learned last class. Guys.
Yes, sir.
Okay, great. Thank you. Kaustubh,
Yes.
Ria, Tom. Yeah, Ali, you're trying to say something? Ali, I think your voice broke in between. Mm-hmm. Mm-hmm. Everyone, are we very
Yeah, is
clear
it
with
better
this
now?
one? Sorry, I was not able to hear you. Ali. Yeah.
Hello, sir.
Yeah, I can hear you now.
Yeah, my question, why for a simple, like when you have just one variable, why there is a difference between adjusted R square and R square when you have just one variable? Simple linear regression.
Yeah, because the formula is different, right? So even in a simple linear regression, the term adjusted R square comes because it kind of, rescales things basis degrees of freedom. So even in a simple linear regression, you will never have both of them to be equal. But if you see, they are quite nearby. So the values will not be exactly same because the formulae themselves are different. So the degrees of freedom also kind of caters or accounts for an adjusted R square. Hence, there's a small rescaling happening at the back end. So you will never see these two numbers exactly coinciding even in a simple linear regression model, broadly. Yeah. So it's not like that, that if it's a simple linear regression, the formulas for both of these guys, R square and adjusted R square, kind of becomes equal. The formulas are different by the very nature, and at every step they remains different. Hence, the answers would be maybe nearby at times, but not exactly equal. Major. Great. Ria, I hope now you're clear what we were trying to discuss last class by the concept of parsimonious. So basically, I'm just helping. Just ask is helping me understand that remove G1, G2, G3. As simple as that.
Yes, sir.
Okay. Anything else, anyone? Can we start with the lecture script directly then? Guys,
Yes, sir. We
can you
start.
be a little active? Others? Okay,
Yes, sir.
great. Okay, thank you. All right. So guys,
Introduction,
yeah,
introduction
Tom.
of more variables won't help the accuracy of the fit. Correct.
Correct. So introduction of more variables will see, it may add to accuracy, but introduction of garbage variables won't add to accuracy. Now, obviously, here it was very clear that G1, G2, and G3 are garbage variables. In reality, when you're genuinely trying to add a rating factor, you would not know whether it's a garbage variable or not. Correct? This is where adjusted R square kind of helps you with the information that whether adding this variable is adding substantial value to the model or not. It is just that one simple question what adjusted R square is trying to help.
Suppose these variables, this if we,
Mhm.
suppose 2-3 exercises are linearly related, then what will happen? Then also this accuracy won't be taken. Won't be the accuracy won't be there. Not much accuracy. If
Yeah,
this
definitely. If you're saying that two excise kind of tells the same amount of information, right? Or it kind of tells the same information, then obviously keeping that another variable would, not be beneficial. So adjusted R square will definitely help you tell that same story. Is that good to go? Okay, great. All right. So guys, we will learn how do we build a linear regression model in R today. Yeah, Anushka.
Means sir, first we find the R square and then we find the adjusted R square after adding that garbage variable. If it is a significant impact our adjusted R square, if we see the change in the value, then we decide we should keep it in the our calculation or not.
Yes,
Like
absolutely. Absolutely. So you would just see whether adjusted R square have increased or it have reduced. It's a two-way call, that's it. If it have increased, keep it in the model. If it have reduced, remove it from the model.
yes.
Okay, great. So guys, how do we start building a linear regression model in R? It's very simple. You give any model name what you would like to give. The function what we will use here is LM. What does LM stands for? Okay, LM stands for linear models.
Linear.
Yeah, LM stands for linear models. And you write down a formula within that function. Now, what do you mean by a formula? You will have to write down your dependent variable or your target variable or your response variable first. Then you separate it by a tilde sign. So this sign, what you see follows to is called as the tilde sign. And then you write down all your independent variables, explanatory variables, regressors. Correct? So if you remember this, or if you remember the code, what I just wrote here, it was the exact same thing. I created a linear regression model. My MPG was the dependent variable, hence it came on the left hand side. Tilde is the sign to kind of separate X and Y. And in this model, I only had weight as my explanatory variable, hence weight. Here I had cylinder and weight, hence it was weight plus cylinder. Here it was weight, cylinder plus the garbage variable. And similarly, I just kept on writing it down. Is the formula of how do you write it down clear, everyone? Guys?
Yes, sir.
Okay, great. So I will just quickly, let's say, take up this model, right? I'm just deleting everything else. I just want this particular model at the moment, right? So this is how you just create a model in R. And obviously, if you just run the modeling part, it gives you the intercept and the coefficient. So this, if you remember, since it's a simple linear regression, my linear equation becomes MPG equals to beta naught plus beta 1 into weight, right? Since our objective in a regression problem is to kind of estimate these two guys, beta naught is nothing but your intercept term, which is 37.285. Beta 1 hat is nothing but your negative 5.344. So these are nothing but your regression coefficients, if you remember from our last lecture what we were discussing. Everyone, simple, good to go till here.
Yes. Yes, sir.
Okay, great. Now, the most important or the most frequently asked section in the exam is to kind of generate a summary and comment on it, right? So let me just quickly run this function to show you guys what all output you have from this one, right? I'll just rerun it so that everything kind of comes on the same page. Okay, yeah. And I'll just zoom in a little, correct. Okay. So if you see, this output is entirely based on the summary of your regression model. This is nothing but the formulae that helps you understand what are the X and Y's in the model. Residuals, if you remember, was nothing but the error that I make in prediction. So if you remember the EI component, where EI was nothing but the delta between actual observations and the fitted observations, right? If you remember that term, what we learned last class. So this is nothing but a quick summary. What is the minimum, maximum, and the median of residuals? Just a quick insight on where the residual value lies approximately, correct? This grid, again, is very important to understand let's try to spend 10-15 odd minutes to understand what all information is saved within this grid, right? Again, if you see, it says intercept, that means beta naught or alpha. Weight was nothing but my regressor, what I have added inside the model. Depending upon how many regressors you keep on adding inside the model, you will keep on having 1111 extra line entry on this particular side of the section, right? If you see on this section, you also have a lot of columns here. The very first one is the estimate, that is nothing but the regression coefficient. So my beta naught hat is 37.285. My beta 1 hat or the regression coefficient associated with weight is negative 5.3445. Can anyone tell me what is the interpretation of this negative 5 point some number? How do you interpret this number? Anyone would like
Slope is negative, no?
Absolutely. Slope is negative. That's right. That's why you see a negative sign.
That is inverse relationships.
Yes, absolutely right. It means there's an inverse relationship, which means as weight increases, my miles per gallon, that is my mileage, would reduce. Yes, that's right. Anyone would like to further? Yeah, Ali.
Yes, I think this is the change that happens in the dependent variable when the independent variable changes by 1 unit.
Yes, absolutely right. Very good. So guys, this number also tries to help me understand the impact or the quantum of impact on my Y. So what Ali was trying to tell is that this negative 5 tries to convey me that if you increase the weight of the car by, let's say, 100 kgs, for example, or let's say by 1 unit, for example, if I try to increase the weight of the car by 1 unit, the mileage of the car would reduce by 5 units. Everything else being equal. Everyone? Guys, is the interpretation clear
Yes,
of how
sir.
do you exactly predict or understand this one? So similarly, this becomes very important, in modeling situations. For example, if I want to understand that in health insurance, if the age of a customer increases by 1 unit, what exactly is going to be the impact in the premium, right? So it is these beta coefficients that helps you comment or helps you understand that when you change 1 unit of xi, what it is that the impact is going to be on your overall y. See if that's making sense, everyone.
Yes, sir.
Guys, good to
Yes,
go.
sir. Yes, sir.
Okay, great. All right, great. So this part, I hope everyone is very clear. Moving on to the remaining 3 columns, that is the standard error, t value, and the p value. Can anyone make a guess what these 3 things are talking about? When do you see a p value and when do you see a t value? In what scenario you would see them?
Hypothesis test. Hello?
Yes, absolutely. Very good. You are trying to perform a hypothesis test here. That is where you see a test statistic value and you see a p value here, right? Absolutely right. Now, what exactly is this hypothesis test? So if you remember, the very first thing in any hypothesis test is that you define the hypothesis. Now here, obviously, they haven't defined any hypothesis. So we will have to know on our own what this test is about. Yeah.
I think they are around estimation of these coefficients.
Yes. Yes. Fair enough. Yes. So guys, here for this particular hypothesis, the null hypothesis goes that your beta coefficient is equal to 0 versus H1 that beta is not equal to 0. Right? Oh, sorry. Yeah. This is the hypothesis test what you're trying to work upon. Now, can anyone try and tell me why 0? I mean, till date, whatever hypothesis test we have studied, it is kind of flexible, right? Beta equals beta naught, mu equals mu naught, sigma equals sigma naught. Why exactly is this test referring to 0? Question number 1. Question number 2, why only not equal to 0? why is my alternative hypothesis not catering to less than greater than? Why it is strictly not equal?
So 0 because you are trying to
Mhm.
say that there is no impact.
Okay.
And not equal to 0 because you are not like measuring correlation. It's only there is impact or there is no impact.
Okay. Fair enough. That's right. So, Ali, if you can further tell me what exactly happens if beta is 0, how does that matter to me? It's okay, right? Just a value. So why am I so bothered about it? Or anyone in the class for that matter. If you guys, so Ali, have correctly mentioned the first or answered the first two questions. But why exactly am I so curious to look at 0? It's okay, right? Even if it's 0, how does that matter? It's a number. It can take any value from negative infinity to positive infinity. How does it bother me? Anyone? Okay, fair. Can anyone help me understand when I say beta is 0? I mean slope is 0, guys.
Yes.
When I say slope is 0, how does a line would look? How will the line look?
Straight line.
Straight line.
Okay, straight line. Okay, fair.
No,
Even
it's like a dot.
straight line, if this is a straight line, when this is a straight line, when this is a straight line.
45 degree. A line passing
45
from
degrees, something like this, passing from origin.
No, if the beta is 0, then there is no existence of, means it is a dot only. Because x is 0. No? If beta is 0, x becomes 0.
Mm-hmm. Okay, fair. Okay, so guys, if you remember your equation, it looks something like this, correct? Everyone?
Yes, sir.
If
Yes,
beta
sir.
1 is 0, 0 into any x you try to cater, I hope you would appreciate this term would entirely be 0.
Yes, sir.
In that case, can I say y is nothing but equal to beta naught? And
Yes.
beta naught will be equal to, it will be equal to y bar, right? Basically, in that sense, what I'm trying to say is that if my data point looks something like this, I will just quickly demonstrate you using a chart so that you guys are able to understand it more clearly. So let's say I have the garbage variable on one axis and I have my miles per gallon on another axis. Let me just expand this section to get rid of the error. Okay. Do you see any relationship between x and y here, guys?
No.
No, absolutely. You don't see any relationship between x and y. In such a scenario, right? Even if I try to fit a model here, and if I try to plot the equation or my fitted line or the regression equation on this particular scatter plot, I forgot a comma here. Do you see how the line is turning up to be? It is almost a horizontal line, if you would say. You do see a very slight tilt over here or a slight angle over here. But I hope you would appreciate that broadly the line is a lot more flattish, right? Basically, this is what happens when your beta is 0. If you try and see the regression coefficient of this model, right, it is negative 1.01. If I further add the data sets or if I further enlarge in the data set, it would kind of move more close towards 0. Is that making sense, everyone? Guys? So
Yes,
if my
sir.
beta coefficient is exactly equal to 0, you would see a flat horizontal line. For example, let's say if I say my intercept is the same, let's say which is 20.16, I'm just copy pasting it from here. So if I say AB line, A is 20.16 and my beta is 0. Let me make it a blue color line so that we can see it differently. You see, this is how the line would look. I hope you'd appreciate that the red and the blue line are not far apart. Make sense, everyone? So the whole perspective of testing this hypothesis is for me to ensure that if at all any regression coefficient is coming up to be insignificant, that is, if you remember the hypothesis I wrote down here, if my beta is 0, then basically it is not adding any value for me. Kindly remove it from the model altogether. Everyone, is this clear what this hypothesis test is all about? It is trying to test about this hypothesis. Again, why it is so much interested in 0? Because if at all any coefficient turns up to be 0, it kind of adds 0 value in the model. Hence, it should be removed. Why I am again so much interested in not equal to 0? Because if it is positive coefficient, if it is a negative coefficient, again it doesn't matter to me. As far as it has some substantial value in building the model, I am okay to keep it, whether negative, whether positive. As far as it is not 0, I am happy as a modeler to keep that regression coefficient within the model. See if this entire story is making sense, everyone. This is very important section because you will see about 5 to 6 marks in your exam trying to help you comment on this section or around this area. Guys, is this understanding of this hypothesis clear, everyone?
Yes,
we are-
but can you please repeat again?
Yeah,
We are-
I'll repeat again. Yeah, Tom, you're trying to tell something.
So we are testing the slope. Slope parameter is equal to. We are testing H naught. Slope parameter is equal to 0. Against is not equal to 0, right?
Yes, that's what you're doing. Correct. That's right.
But yeah, the slope parameter. If you're testing, if you reject the hypothesis, that means there is that it is significant. Slope parameter is
Yes.
significant. Right.
Yes, absolutely. It means that it is significant. It is adding some contribution towards my model. Yes.
Otherwise, it is not at all doing anything. Like if it
Yes.
is-
Otherwise, if you see this chart on the screen, that is what it's doing. It's a flat line, not helping me at all. Ria, I hope that helps.
Yes. Sir.
So if you kind of try to calculate a correlation coefficient here between the two guys, you would see the correlation also being very weak. So if I just write empty cars dollar MPG, comma empty cars dollar G1, see it's coming to be a very weak correlation, less than 10% if you see around this one. So if you remember, right in our first lecture we discussed, right? I don't know if you remember, I told you that the whole reason you study correlation first and then regression is because if there is no relationship between my two variables, take it any model in the world, it is not going to work for you because the model does not have any patterns or any trends to pick up. If you see here, a straight line means that irrespective of how G1 moves, miles per gallon have nothing to do with it. That's why you see a random scatterness. So it doesn't matter what G1 takes. Your MPG can take any value. It's basically non-predictive. That is what this information is trying to tell you. So just to again reiterate for Anushka, when I say beta is 0, basically I'm trying to ask via hypothesis test that is this estimate 0? If at all this is 0, since I know that beta coefficient into its respective xi's, again for me to write down the equation for you guys, it is y equals beta naught plus beta 1x, right? Since this guy is 0, 0 into anything is 0. So this complete term wipes off. It only becomes beta naught, right? So in such a case, whatever value x takes, I don't care. Hence, it doesn't make sense for me to keep the x. Remove the entire equation from the model altogether.
That means that is an equation that is an y is equal to beta. Beta 0 is the equation parallel to x-axis, right?
Correct. That's what we have done over here, right?
Yes.
So beta naught basically becomes y bar in this scenario. That's what you have over here if you see. On the chart on the right hand side of my screen.
But the intercept parameter is of not much significant, nah?
Intercept parameter in some situation it is, but right now we are not too much concerned on the intercept part. So we are only focusing on the excise ka coefficient. I'm not too much interested in on the intercept part. But in some scenarios, intercept is definitely also of importance. Yeah, Ria.
So I just have a basic question.
That's okay.
Maybe so like in PS we studied y hat is equals to alpha plus beta x, right?
Correct. That's right.
I got confused between beta naught and beta 1 here. Like, is that the
Ah.
same representative of that?
Yeah, fair. I'll just help you clarify that. So when I write beta or in this expression beta, it is nothing but that coefficient only. So if you see this estimate, matlab, don't try to, matlab, it's okay when you're getting confused, but don't try to think it in that fashion. Just think it that, okay, this estimate is with respect to alpha or the interceptor. This estimate is with respect to WT or the weight parameter. So this is applicable for all coefficients, alpha, beta naught, beta 1, beta, gamma. Take it any coefficient name what you want. Because the test is being performed for every estimate here if you see. It is just a notation what I've just given it over here. The context is of more prime importance. That whether it is 0 or not is something what I'm very curious to understand about.
So like coefficient, by coefficient we mean like the value
Estimated value.
estimated. So like the value that x has, right? Like the coefficient of x. That is the coefficient, or like
Okay.
I am confused.
So when I write y equals alpha plus beta 1 into x, let's say. So whenever I say coefficient, see, that's why it's very important to have the definitions very clear. Y is my response variable or my target variable or my dependent variable. Alpha and beta over here. Even let's say if I have beta 2 here for that matter into x2, x1, x2 are my regressors, are my independent variables, are my explanatory variables. Apart from these two things, whatever you see on my screen, beta 2, beta 1, beta 3, gamma 1, gamma 2, gamma 3, alpha, alpha naught, beta naught, anything what you see are regression coefficients, right? So anything that is associated with your explanatory variable is nothing but your beta coefficient or regression coefficient or parameters, whatever you want to name it.
Yes, sir.
I hope that's clear. Anushka, I hope the understanding is clear on this part now.
Yes, sir.
And to everyone else as well. Guys, are we very clear with this? Okay, thanks, Ali. Others?
Yes, sir.
Okay, great. Bhavani, are we good to go?
Yes, sir.
Great. So moving on next to the same summary now. I'll just go to the bottom half first. I don't want to confuse you guys more. So I'll just take up the easier part first and come to the difficult part at the very end. Okay. This statement says residual standard error. Any guesses what is this term? What do you mean by residual standard error?
This that residual, that yi minus y cap, that error standard error, no?
Okay, fair. So guys, in regression, there is an assumption. The assumption is that your residuals, EI, follows normal distribution with mean 0 and variance sigma square, right? If at all you don't remember the assumption, that's fine. Just note it down at the moment that you have this assumption in your books that the residual follows normal distribution, correct? This is an assumption with mean 0 and variance sigma square. Now, obviously, this variance is something what we will not know always, right? So if I don't know the variance, what do? We estimate the variance, right? So obviously variance is sigma square. Standard error is nothing but sigma. So this term, what they're trying to talk about, residual standard error, is nothing but the standard error of this term. EI or the residuals. So that estimate is 2.968. Makes sense, everyone, guys?
Yes, sir.
Yes, sir.
Yeah. Great. All right. Next, you have R square and adjusted R square. Both of these things are something what we have already discussed now. Everyone, simple, good to go.
Yes, sir.
Great. Coming on to the bottom part now, it says F statistic something something and the p value. Again, if you see it's a p value, it means it's a
Sir,
yeah, Tom.
here adjusted R squared is marginally less, correct?
Correct.
That doesn't matter now. It is of no use. Like that fit is
Yeah,
good.
correct. Adjusted R square. Here broadly you can, since it's only a simple linear regression, it's
Yeah,
broadly good enough.
only two parameters like.
Only two parameters, but only one regressor.
Yeah, correct.
So if I add another regressor and whether that is, leading to a garbage or not, that is where I would be interested to see if adjusted R square have fall or increased or whatever is the relationship.
Most
Broadly, I'm good to go as
of
a
the two
second.
parameter linear regression, this adjusted R squared and R squared will be almost equal.
Yeah, it should be marginally on the same page. You will not see something like a 75 or 50.
Okay.
Right? They would be marginally almost around the same vicinity. Okay. Fair. Guys, moving on to the bottom part. This is again a hypothesis test. Now, obviously, when I say hypothesis test means it will again come with some H0 and H1. So I'm again writing down the hypothesis. See if you guys are able to explain me what this hypothesis is all about.
We are going for a k variable set. No, k parameters are there.
Okay, fair. So this is the hypothesis what I've written down. Take a couple of seconds and see if you guys are able to explain me what do I mean by this, or what is this hypothesis exactly trying to calculate or tell me.
The hypothesis, null hypothesis, all are equal to 0, but in at least at one of the parameters is not equal to 0.
Fair, but what does it try to tell me then?
There is one
that is
parameter
mean-
which has got it has alternative hypothesis will be correct. Like we reject the null hypothesis. At least one should be one should be we will be reject at least for one. At least we won't be rejecting it. Correct.
Correct. Yes. Yes. Fair enough. Good. Yeah, Ali.
Like, is it about like all these variables does not have any impact on the dependent variable? Against they have impact.
Yes. Yes. Absolutely right. Good, both of you guys. So guys, this hypothesis, what I've written down, is called as a global test or global testing, right? What do I mean by global testing? It simply means that you kind of question the entire model, right? So if you have a model with 10 xis, you kind of question the existence of the entire model, right? So the null hypothesis says that all beta coefficients are zero. Now I hope you would remember when I say all regression coefficients are zero, it means that if I have beta 2 into x2 and I say beta 1 and beta 2 both are zero, again you come down to the same picture, y equals beta naught, right? This is again kind of wasting time in modeling because none of your xi's are helping you model y. So instead of looking them at individually, is beta 1 0, is beta 2 0, is beta 3 0, is beta 4 0, a global test gives you one single answer whether at least one x is helping you predict y or not. So since here you have weight that is coming up to be significant, here also you see p values very small, which means that you reject your null hypothesis and say that at least one beta I is significant. right? Then obviously you will go to beta 1 to see if this is significant. You will go to beta 2, beta 3, beta 4, beta k to understand which regressors are helping you model X or model Y for that matter, and which one of them are not helping you model Y.
At least one beta one. I think it can be beta one,
Correct.
beta two, beta one, beta three,
Exactly.
like
That's
that.
why I wrote beta I here. So it can be any one or at least one out of all the case. Now, whether it is 1, 2, 3, 10, or whether it is beta 1, beta 8, beta 6, I don't know that right from this hypothesis. I will have to go individually and test what we did right here in this section of the hypothesis. Guys, see if this is making sense. Everyone.
Sir, can you please repeat the whole statement of null hypothesis?
Yeah, I'll do that. So if you see the null hypothesis, I am saying that whatever beta coefficients I have in my model, right? Just now I mentioned, right? All your betas are nothing but the coefficients, the regression coefficients. In this case, I am saying all of them are equal to 0, right? Now, when I say all of them are equal to 0, I am saying that 0 into x2, 0 into x1, 0 into x3, 0 into x4, whatever it is the equation. Now we learned that anything that is 0 into is kind of not helping me. So if all of my betas are 0, can I say that the model is useless or garbage? It again boils down to beta naught, right? So instead of me going to each beta and understanding is it 0, is it 0, I hope you would appreciate if you have thousands of xi's. You will not go to each of those 1,000 betas to see are you 0, are you 0, are you 0, right? So instead of me looking at each of the 1,000 xi's or their regression coefficients, is there a way that directly tells me all 1,000 are garbage? My works become simpler, the amount of information I see becomes smaller or lesser. That is what this hypothesis called as global hypothesis testing or the global testing is helping me understand. If my H naught gets accepted, basically I'm saying all regression coefficients are 0. Basically, it says that the model what you have made is a garbage model. Don't look within it because all xi's are not helping you predict y. Correct? If at all you accept H1, you are saying that out of beta 1, beta 2, beta 3, beta 4, beta k, whatever it is, at least one xi is helping you predict something. Right? So in that case, the answer is that you go inside the model, you go to the summary, and then you try to see which xi is helping you predict. So it can be one xi, it can be two xi, it can be couple of xi's, it can be x1, x2, x4, whatever it is. That information will help you understand from this particular summary over here. Yeah, I think someone raised their hand. Yeah.
No, sir, I only raised the hand.
Yeah.
My basic question is why? What is our hypothesis? Means I understood that our main hypothesis is that beta 1, beta 2 all are equals to 0. This is
Okay.
our null hypothesis. And our alternative hypothesis is that key at least one beta is equals to 0. Then also our model is works. H naught says all should be 0. Then
Correct.
only model works. And
Then model is
beta
not
1.
working. If H naught says everything is 0, then the model is not working for you.
So means what is our main what is our claim of the hypothesis? I am not understanding.
See,
What is we are claiming to?
okay, fair. Let me give you another example here. Hmm. Do you appreciate, or everyone, do you appreciate G1, G2, G3 are garbage variables? Guys, yes, no.
Yes, sir.
Yeah. Give now this is because you know that the variables you created in the fashion that they are garbage. In reality, when you're actually trying to solve a problem, you will not know whether it's a garbage variable or not, right? So if I want to understand whether your CIBIL score impacts the frequency of own damage claims you make under a motor insurance portfolio, is something what I'm genuinely trying to test, right? I don't know if it's a garbage variable or not. So here, let's say I have 3 XIs in the model, G1, G2, and G3. Now, again, if you try to see the same summary of it, I am just looking at the bottom for now. So given the hypothesis, Anushka, would you reject the null hypothesis or would you accept the null hypothesis?
If all are garbage variables, we'll be rejecting the null hypothesis.
X
No,
not
I'm just
rejected.
looking at the number. Look at the p-value and tell me, would you reject or accept the null hypothesis?
Accept the null hypothesis.
Good. Accept the null hypothesis because my p-value is more than 5%. Very good. Now, if you go back to the hypothesis testing, what we're trying to do here, when I say that my null hypothesis is accepted, I'm saying all of my betas are 0.
Yes.
Yes. So this test is basically telling you that since all your betas are 0, don't spend time investigating G1, G2, and G3 individually. That is also what you see here, that all the p values are more than 5%. Again, the individual tests are also trying to tell you the same story, that G1, this number is insignificant. This number is insignificant. This number is insignificant. Right? Again, if you remember, when I say it is insignificant, it is 0 into G1, 0 into G2, 0 into G3. So if everything is 0 into, why do I want to keep it inside the model? It's useless to have such a model, right?
Yes.
Correct. So this is what this test is trying to tell you. If you have G1, G2, G3 up to G1000, will you go at each of the cell and look at 1000 cell, or you would want one number that tells you the same story? If I want to communicate a message to you, would you prefer it in a one sentence or would you prefer it in a textbook format?
One sentence.
In one sentence, right? That is what this hypothesis is doing for you. It tries to tell you in a one number way whether all these variables are garbage or not. Now, obviously here, since there are only 3, it is very easy to look at visually and comment, right? When it comes to real world or real practice, you have more than 200, 250 XIs in the model. I hope 200, 250 is not very easy to just have a quick glance and comment, right? Hence, this hypothesis test becomes very important to quickly understand whether the model is a garbage model or there are some XIs that helps me predict why. If at all there are some XIs, now I would come here to investigate as to which are those XIs, what is the impact, to what extent is the impact.
Yes, sir.
Yeah,
But to get that exercise, we had to take another test is there, paired test or something.
exactly. So this test what we're performing, right, is called as the individual testing. That is why I termed this test as global test. I don't know how many of you guys also noticed the test statistic here is t value, which means you are using a t distribution here. This one is an f statistic. So this guy works on ANOVA. If you guys have learned ANOVA, then it's okay to relate. Otherwise, just forget what I just mentioned. That's completely fine. Guys, are we good to go till here?
Yes, sir. Means global test gives us both the t value and f value. Means both hypotheses in this one work.
No. They are
ANOVA
not
is for
giving you-
global test, no? ANOVA is for global test, right?
Yeah, correct. This one is for global test. Yes. So Anushka, to
Basically,
answer,
this regression also we are taking on ANOVA.
yeah, correct. This one is helping use. This one we're kind of concluding using an ANOVA analysis. Yeah, absolutely. So Anushka, just to answer your question, you are not kind of combining T and F. I mean, let's not go in that direction. You're not combining. These two tests are completely parallel and independent tests. your global test is just telling you whether you should go to individual testing or not. Since
No, sir, that I understand. They both are
Mhm.
individual tests, but I was
Correct.
like, ki, we have a function in R or we have code in R that in a one code we perform both the tests. As it is
Yes.
like that, that is my
Yeah.
question.
Yeah. That's absolutely right. You just have to use the summary function to perform both of these things. Nothing else required.
Okay, thank you. I understood.
Okay, great. Chalo, others, are we good to go?
Yes, sir.
Yes, sir.
Okay, great. So with this, the bottom section gets over. Now, given I am very scared to introduce these tasks to you guys, so I'm thinking whether I should introduce or not at the moment. But okay, let's give it an attempt. Let's see if able to understand.
Sir,
Okay.
global test is over. Now, you told no, there are some individual exercise. Coefficients are there, but more representative. So, is there any test for that also? No.
Any test for what?
See, global test, we at least one exercise are important, right? In
Correct.
global test. So, which
Correct.
exercise is more important? We have to do some kind of other paired. Each pairs we have to see or what?
No, no. You are saying it right. You're going in the right direction. Which, here it's not pair. Here it is individual only.
Now, global it is individual, but when we test which exercise is very
This is
important.
what you have, right? This is what you have right here on the screen. What I've highlighted. This is what is the information that will tell you which of them is significant. Okay, I'll help you. I'll help you with that. Let me take another example. So let's say instead of G1, G2, and G3, I also add weight. Right? I execute the model. Now, if you see, the p-value is less than 5%, everyone. So I say that I reject my null hypothesis. Now, when I reject my null hypothesis, I say that at least one beta I is not equal to 0. Now, sir, which beta is not equal to 0? I don't know. At least I have that confidence that the model what I have built is a significant model. It helps some xi. Now, it can be 1 xi, 2 xi, 3 xi. Which xi? I don't know. There is something in the model that is helping predict. Right? This is what I conclude. Now, to answer your question, Tom, which is that xi and how many xis? That is why you have this grid sitting over here. So now you see G1 and you say that, oh, the p-value is more than 5%. It is a garbage variable. Garbage variable. Garbage variable. Oh, this is that regressor since its p-value is less than 5%. This is the regressor that is helping you predict y. So now, once you are confident that, okay, there is someone helping me predict y, the very next stage is to go and understand which is that x or how many of those x. I hope you guys are able to follow the sequence. The very first thing is to understand whether things will follow or not.
Yes, sir.
I hope that's making sense, right?
Yes, sir.
I will put it in a very simple way. Okay. So let's say if you come to college. So if I what would be more better? If I tell you that there is a no lecture and you guys don't attend, or if you attend the lecture and then I tell you, okay, there's no lecture today. What would you prefer? Would you, if I do that in tomorrow's 7 a.m. lecture, let's say that you all come for the lecture and say there's no lecture, guys. Would that be preferred? Or would you prefer me telling it way before that there's not going to be any lecture tomorrow?
The second one.
The second one, right? Obviously, it's the same story here. The global testing is clearly trying to tell you whether you should spend time inside these buckets or not. It is just trying to tell you in what direction you should go. Should you go towards model building or you should just come out of it, saying that it's all garbage now? There's no point in working around it. That's it. Nothing else. Guys, are we clear with this one till here?
Yes.
Yes, sir.
I don't know. Someone said something at the last. I couldn't get that. Okay, great. Assuming everything is good to go. Okay. Now the last bit of this section, everyone, is talking about these stars, what you see on the screen. Please pay very close attention. If I have to repeat this, it would be a very, very big task. So let's try to finish this in one shot, right? Everyone with me, concentration level at 100%.
Yes.
Yes, sir.
Okay, great.
Yes.
So before I move to that thing, I will ask you two questions. Okay. And you just have to answer as to what is your opinion or what is your view. Okay. If I reject H naught at 5% level of significance, okay, will I reject H naught at 1% level of significance? Yes or no is what you have to answer.
Yes.
Okay, Ali said yes. Others?
The area under the 5% contain the area under the 1%, you know. So it will be that rejection region will be reduced.
Tom, so I'm saying if, so let's say if I reject H naught at 5%, does that imply that you will also reject it at 1%?
Yes.
Might not.
Not really.
Not like it might or might not.
Okay, fair. Others?
5% contain the 1% also, no? 5%, 0.5 that area, and but is
Mhm.
0.01%, you know, 1%.
Okay. See, the best thing is to take an example. Let's say my p value is 4%. If p value is 4%, do you reject H naught at 5%, Tom?
No, it's accepted. No, we don't reject it. It will be 5%, you know.
Yes, it will
P
be.
value is 4%. It should be, if 5% is greater than, no, we won't reject it.
No. So Tom, if you remember, if p value is less than alpha, then you reject it.
Yes.
So 4% is less than 5%, right?
No,
4%
p
is-
value, that actually p value, p value should be greater than 5% is greater than 4%, no?
Correct. So the definition
Yeah.
is if p value is less than alpha, then you reject the null hypothesis,
Yes,
right?
yes.
So is 4% less than 5%, which is my
Yes,
alpha?
we reject it.
Yes, you reject the null hypothesis. Great.
Yes.
So now I'm saying, since I reject in this scenario, will I also reject if my alpha changes to 1%? So now if
Yes,
my alpha goes from 5 to 1, is 4% less than 1%?
yes.
No,
No, right? 4% is more than 1%.
Yes, yes, sir, correct.
So is this statement what I wrote down over here? Is this true?
So false.
Absolutely right. Yes, good. The answer is false. Everyone, are we very clear with this statement? The statement what I've written down over here is completely false. Everyone?
Yes,
yeah.
sir.
So, can there be any one case where at both level of significance?
Obviously, you will have some cases where, so if I let's say make the p value as 0.00001%, then obviously in that scenario it holds true. But right now I'm asking it, can I declare it as a universal rule?
No, that cannot be.
Absolutely. I cannot make it as a universal rule.
It
Right?
depends on the alpha, no?
Correct. It absolutely depends on the alpha. Now I am just changing the statement. Again, tell me if the statement what I've written down is this universally true or not? So
Yes.
now the statement is reversed. Instead of 5% implying 1%, it is now 1% implying 5%. See if this is
True.
see what is your view on this one?
It's true.
Yes, it's true.
Sorry?
It's true.
Yes. Everyone, this will universally hold true. Right? Everyone, is this
Yes.
very clear? Any questions on this one? This is universally true. Let's say if I want to further complicate this statement. See if you agree with this statement. If I reject at a 1%, that means I will reject it at 5% as well, and I will reject it at 10% as well. See if this statement is
Yes,
also
sir.
universally true.
Yes, sir. True.
Yes, sir.
Everyone crystal clear with this?
Yes, sir.
Yeah.
Okay, great. Now we did so much of efforts to understand this statement is for me to tell you that if I reject a hypothesis at a particular alpha value, then I will reject that hypothesis at all alpha values that are beyond that alpha. What I mean is, if I reject at 1%, then I will reject at 1.5%, 2%, 2.5%, 5%, 10%, 15%, 30%, 50%. Everyone?
Yes, sir.
Yes, sir.
Yes, sir.
Yeah. So what I'm saying is that if I reject alpha at some threshold, any alpha value beyond that threshold, my decision will not change. Are we crystal clear with this statement or with this line?
Yes.
Yes, sir.
Now, with this statement in mind, I am coming to this particular grid as to what these star indicates. Okay. Now pay very careful attention. Whenever you see 3 stars, it means alpha is 0.001, what you see on my screen. When you see 2 stars, it means alpha is 0.01, that is 1%. When you see 1 star, it means alpha is 5%. When you see dot, it means alpha is 0.1 or 10%. Okay. So what R is helping me say over here is, instead of me looking at individual p value and then trying to compare if it is less than 5%, less than 5%, less than 5%, R gives you these stars to directly or intuitively comment whether this intercept or this hypothesis or this regression coefficient is significant or not. Okay. How is R able to tell that is, if you see 3 stars, it means that this hypothesis gets rejected at an alpha value as low as 0.1%. Correct? If you see 2 stars, then R is trying to tell you that this hypothesis gets rejected at as or an alpha value as low as 0.1%. Sorry, 1%, not 0.1%, 1%. If you see only 1 star, like you did here, okay, we never did an example with 1 star. Okay, let us do that then. Not a problem. Let me just add all guys, and here we are. Okay. So if you see, you have 1 star here. So if you see the p value, everyone over here, will this hypothesis get rejected at 1%?
Yes.
Yes, this will get rejected at 1%. Guys, the p value is 1.1%. Is 1.1% less than 1%?
No, sir.
No. So this hypothesis does not get rejected at 1%. Will this get rejected at 5%? Yes, this hypothesis will get rejected at 5% alpha. That's why you see 1 star. Right? If at all this hypothesis was expected to be rejected at, let's say, 1%, you would see 2 star corresponding to it. You would not see 1 star. Right? If you see this hypothesis, the p value is less than 1%. That's why you see 2 stars, 3 stars, 2 stars, a dot. Right? So instead of me looking at every p value individually and then trying to comment whether it is significant or not, R gives you these stars to helps you understand directly by looking at the table as to which regressor is significant, right?
For different alpha.
Yes, for different alpha, but obviously your alpha is the same. So the for example, my alpha in my study or in my research is 5%, right? Now, basis 5% in this grid, I have to look for at least 1 star.
It
1
depends on the
star, I
question.
am happy. 2 star, again, I'm happy. 3 star, again, I'm happy. I don't care how many stars do I have, but I have to see at least 1 star if my alpha is 5%. If my alpha is 10%, then I am interested in seeing at least a dot. So a dot, a star, or any number of star is something what makes me happy, because then I'm seeing my hypothesis is significant.
If the question doesn't particularly say the significant level, then we have
Then
to
it's
see
5%. Then it's always 5%.
5%.
Yeah. Yeah.
Then we have
So
to select those only.
yeah, absolutely. So whenever alpha is 5%, you would come here and see for at least 1 star. So for example, if you see this variable, horsepower is a significant regressor. Weight is a significant regressor. Cusack is a significant regressor. And automatic is also a significant regressor. These two variables are significant at 10% alpha because you see a dot here. So I'm not interested in that because my alpha level is only 5%. So I would not consider these as significant. But just by looking at the dot, you have an understanding that if my alpha was 10%, they were also significant. So instead of looking each number individually, I hope you would appreciate you see something 10, 11 variables on my screen, right? So looking at each p-value would be very, very tiresome and cumbersome. Just by looking at the star, I can immediately tell there are 4 regressors significant at 5% alpha. At 1% alpha, 2. At 0.1% alpha, only 1. At 10% alpha, 1, 2, 3, 4, 5, 6. You have 6 regressors significant. So the time in which you're able to make the decision or comment becomes very fast or substantially quicker by looking at the stars or dots. Guys, is this helping you guys? Was it clear? Okay, thanks, Ali. Others, it's okay if you think you want me to repeat anything, you can let me know. Everyone else, guys, are we clear? Okay, thanks, Bhavani. Thanks, Tom.
No, the thing is that everything is given at a particular significance level. We have to select our this thing only, correct?
Exactly. At a particular level of alpha, now we have to select what do I want to pick it from.
In the exam, if we don't keep, we assume it is 5% significance level.
Yeah, that is a standard benchmark across the globe. If nothing is given to you in the question, you always consider alpha as 5%. Guys, is this good to go? Others? Is this clear, everyone? Guys, this is very, very widely asked in the exam. Are we clear? How do you read the summary?
Yes, sir.
Right
Yes,
from
sir.
this coefficient to the bottom global test here.
Yes, sir.
Yes. Chalo, great.
Yes, sir.
Okay, great. Thank you. Let's take one exam question, everyone, then. Guys.
Yes, sir.
No. Okay, great. Chalo. So I will solve one question first for us to get some confidence, and then I will obviously give some questions for you guys to work upon. Okay, we have a very simple question here, 5 marker. The question what you see on my screen is October 24 attempt IEQS paper. I will put the snippet in your chat box. Again, that is also a random luck if it will get pasted or not. So I'm not sure. Okay, it's not being pasted. So I don't know, it works very randomly. Okay, it's not pasting anyway, so not a problem. Okay, the question says, again, don't type with me, guys. Since it's our first question, let me do it. You can just see and help me. Use the inbuilt dataset iris for this question. An actual student, blah, 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 wants to understand the relationship between sepal length, petal length of different flowers. In particular, he wants to fit the model. So it's a simple linear regression. Very well written here. Where yi is sepal length, xi is petal length of each flower. Okay. EI follows normal distribution with mean 0. We just learned that this is nothing but the general assumption, right? The first question says fit the required linear regression and show the output. Okay, so that is very simple. How do you create a regression model? You create by writing LM function. Sepal length is my yi. So sepal dot length is my yi. Tilde so that I can write my x on the right hand side. That is petal length. So it's petal dot length. All right. The data is coming from iris, so I'll also have to write that down. The question also says to show the output, which means I have to show the summary of the model. That's it. That's it for 2 marks. Simple. Good to go, everyone, till here.
Yes, sir.
Okay, great. All right. The next question says calculate the confidence interval for beta and comment on the significance of petal length in predicting sepal length. Okay. So to calculate the confidence interval, I'll just write down the subpart. It was, I think, A. This is subpart B. For you to calculate confidence interval, again, it's a very simple thing. You have a function called as confint, standing for confidence interval. You use the function and supply the model within it, right? So when I write confident or model, it gives you a confidence interval for the beta naught, that is the intercept term, and the beta 1 term, right? Given this confidence interval, can you guys comment on the significance? Anyone would like to comment? So is the beta coefficient, is the regression coefficient of petal length significant enough when I'm trying to predict sepal length?
Yes, sir.
Yes, sir.
Yes, absolutely right. Good. Since the confidence interval does not contain 0, right? It means that the regression coefficient for petal length
Significant.
is significant. Significant. Hence, petal length should be retained within the model. See if this is making sense, everyone. Yeah, Ria, you have anything?
So like the confidence interval, like
Mhm.
like the zero value can be in the between the interval, right?
Acha. So if you see the interval goes from 0.37 to 0.44, do you have 0 within this interval?
No.
No, right? That is why you say it is significant, because the coefficient 95% of the times your petal length coefficient would not take a value of 0. Right? Since the interval does not contain a 0, you say that the beta coefficient is significant. That is, it will take some value that is not 0. Since it is not 0, I don't care now what value it is. It is substantial or significant enough for me to keep it inside the model. See if that's making sense.
Yes, sir.
Others, are we good to go with this?
Yes, sir.
Great. The C part says state the R square for model fitted in A. Now, again, you can just go back to the summary what you have created over here. This is nothing but the R square value. You can just copy paste it within the word. So 76% is the R square value. Again, if you see, we learned at the end of unit 3 that you can comment any hypothesis looking at the confidence interval. See, here we wrote the comment that petal length is significant. The same story or the exact same conclusion is what you get looking at the summary over here also. You see 3 stars, which means that at 5% alpha, you accept that petal length is a significant variable. That means it adds value while predicting sepal length. Are we very clear with this, everyone?
Yes, sir.
No, you're not clear.
No, sir. Clear.
Acha, okay, great. Others?
Yes, sir. Clear.
All right, great. So, simple 5-marker question, everyone.
Yes, sir.
Great. So, let's take a quick 10 minutes break here and let's come back to solve more exam questions before we move on to solve, let's say, or learn more concepts. Okay, so it's almost 45. Let's connect back at 56 and then let's take more questions to solve this thing up. Simple, good to go, everyone.
Yep.
Okay, great. Chalo. See you at 56. Bye bye. All right, it's 56, everyone. Can we start? Guys, are we back?
Yes, sir.
Okay, great. So let's try to solve another question, right? Again, I will solve it first. And then if you guys want some time to write it down, you can take that. Correct. Great. So this is an IFO's exam question from 2019 April attempt. We have studied such that we can solve up to 5B, and I think that is more than enough for us to solve for the moment. Great. So I'll just read out the question again. Just try and help me solve it. Don't try to type it along with me. If you want, I will give you guys time to write it down on your own pace. So it says a statistician is carrying out an exercise to analyze a data set that describes the failure times of outdoor telephone cables, okay, with respect to the quality of the cable and the level of rainfall that cable is exposed to. Fair enough. The data is given in this particular file that shows failure time for 20 different cables. Okay. All right. So the very first thing in the question is we'll have to import this data set cables underscore dataset.csv. If you remember, there was this one folder which I shared with you guys stating past exam papers data, something like that. Within that, if you see this particular file, INF CS1B 2019-04 cables dataset, this is the file they're talking about, right? So I'll quickly import that dataset. Again, don't try to type it down with me. Just try to help, if you remember the syntax. So how do you import a CSV file? What function do you use to import a CSV file?
Read CSV.
Very good. It's read.csv. Next.
And you write the path.
Okay, I write the path, but if I don't want to write the path, then
File numbers.
yes, very good. If I don't want to write down the path, I use a function or a shortcut called as file.choose. And obviously you will have to give it some variable. Let's say data equals to. I run the program. I have the screen open up. I can just go select wherever the file is, select that file and press open. If I see my environment, I have the 20 years information already sitting here, and whatever is required is right within R now. Simple, good to go, everyone. Data importing, if you see 0 marks for that. So in case you fail to load the file in your exam, technically the entire subpart is something what you won't be able to do. Hence, it is very important that you revise and you're thorough with each and every smallest concept of R. Right? Great. Question 1, subpart 1. All right. It says fit a linear model to the data with failure times as response, including cable material and level of rainfall as your covariates. Okay, so they want me to make a model. Since they want, or they have clearly specified to make a linear model, we always know, or we already know that it's a linear regression model. So LM is the function name. LM stands for linear model. So they want me to model failure time Since it is my dependent variable, it comes on the left hand most side. Now I want to specify my independent variables, hence the tilde sign would come up here. Data dollar material type plus data dollar rainfall. So at the end, I can just write that the data is nothing but my data variable. Your answer should include a summary of the fitted model. So this is my model, and my final output should also contain the summary. I just quickly run this much to see if there are no errors. There are no errors. So it's working good, all neat and clean. First subpart is done. Guys, do you appreciate simple, short and sweet?
Yes, sir.
Yes, sir.
Great. All right. So my part 1 is done. Simple enough. Let's start with part 2. Part 2, there's subpart A. So I'll just write down that. State the formulae of the model fitted in part 1, clearly explaining the notation you use.
Y
Okay.
is equal to alpha plus beta x.
Yes, very good. Y equals alpha plus beta x.
Beta 0 plus
I have,
beta.
yes, absolutely right. Since I have the value of alpha here, I will write that down. Since I have the value of beta 1 as well, I will again write that down here. Let's say into x1 plus this into x2, right? The question also says that clearly explain the notation you use. So I'll have to clearly define that my y represents failure time. Correct. My x1 represents material type. Your x2 represents rainfall. Correct. If you again further want to just go and write down that, this value kind of represents the intercept, and these two values are nothing but your regression coefficients, that is also completely fine. So these two represents regression coefficients. See if that is making sense.
Yes.
So is the part 2A clear, everyone? Simple, nice and sweet.
Yes, sir.
Okay, great. Let's move on to part B. Part B says comment on the significance of the parameters fitted in model part 1. Okay. So part 1, this is what it is, what I have on my screen. Yeah, I would ask or I would request you guys to comment on this particular
Intercept
part.
and type material are significant. Other things, rainfall is not significant, right?
Fair. But then let's say if it is a 3 marker or 2 marker question, would you only write
Yeah.
this much?
Then we have to set. We can neglect the rainfall, and we have to put a. We have to take a new, and then we have to find R squared and adjust R squared. R squared we have to find adjust R squared to find. Then we
No,
found that
it is, the question
rainfall
is only to comment. So you don't have to find out anything. You just,
then we
you just have
remove
to
that rainfall data, that x2, and then we y is equal to that intercept plus drop, first drop, material drop only.
Okay. Okay. Fair enough.
Wow.
So guys, since anyone wants to further add up over here? Yeah, you want to
Yeah,
say?
I wanted to say let us look at the global test first, and after that, if it is significant, then we could explain further, looking at the other coefficients.
Fair enough. Fair
The
enough.
P value.
Yes. So I just quickly write it down. So we know that if the P value is less than 5%, then we reject H naught. Correct? Everyone?
Yes.
In our summary,
Yes, sir.
we see that for the intercept term and the coefficient associated to the regressor material type, we see that, thank God. We see that the p-value for intercept is less than 5%. Hence, these regression coefficients are significant. Hence, should be retained within the model. Guys, see if this makes sense.
Here for all the values, it is significant, you know.
No. So again, if you see for rainfall, there are no stars
Yeah,
over here.
not rainfall, 0.01, 0.01, 0.05, and all these things, so that intercepted material are insignificant now for all the alpha, except
Yeah.
that one.
Yes.
Except-
So since nothing is given in the question, my alpha is 5%. So
Yeah.
at 5%, I should see at least 1 star. So even
Yes.
at 3 stars, I'm good to go. So rainfall is insignificant. So the same statement you will write down, copy paste, and reverse it for rainfall. So for rainfall, it would become, let's say,
Yes.
in the summary, we see that the p value for the coefficient associated to regressor rainfall is more than 5%. Hence the regression coefficient is insignificant, hence should be released from the model. See if the commenting helps you guys. Everyone, 2A, 2B, simple, good to go.
Yes, sir.
Yes. Chalo, great. Can I move on quickly to subpart 3A? Guys, are you with me? You want some time to settle down?
For me, it's good to.
Okay, thank you. Others?
You can move on, sir.
Yes, sir.
Yes, for what?
Next.
Okay, great. 3A says plot the residuals of model in part 1. Okay. So if I want to extract the residuals, before that, if you remember, residuals are nothing but EI, the error term. That is technically given as yi minus yi hat. Right? So if I want residuals, I just write model dollar. So if you see, there are multiple elements that I can extract from the model. If I write model dollar residuals, I will get all the residuals corresponding to each of the exercise. Since they are asking me to plot, I will just quickly plot them out using the plot function. Figure margin is too large, so I will just expand this section and again run the same program. So this is what the chart, what you have on the screen. Again, in exam, you will have to kind of give a good Y-label, give a title to the chart. I'm not doing it at the moment because that is something what we have already learned. Yeah. So this is the chart. So question 3A is kind of done. Question 3B says comment on the same. Yeah. So I would again open the floor for you guys to comment looking at the chart. Yeah. Go ahead, everyone.
It is a if you plot a center line, that residuals lie in between the lines, that in between lines, right?
Fair. So let me
Because
add
if you put a center line here, so we put all the lines or the dot points are in between, like between on the same side, different side. Correct.
Fair. Correct. Good.
So
That's
that
number one. Good. So just to summarize what Tom is trying to tell, he's saying that the errors are kind of scattering and the errors are kind of scattered around 0. Fair. That's point 1. Good. Any other point you are able to see from the chart?
one extreme point, one
Yes.
outlier is there. Outlier point.
Very good. There seems to be another data point that seems to be an outlier, which is this point on my screen. Very good. Point number 2. So I'll just also quickly just keep writing in the chat box. Point 1 is errors scattered around 0. Yeah. Point 2 is one outlier. Anything else?
Then points are residuals are distributed around the 0 with the constant variance.
Okay.
This is mean 0 and normally distributed with the constant 0 and 0 and constant variance. Like
Correct. So for you to comment on constant variance, Tom, there's something called as a residual chart what you have to use. This is not a residual chart. So
yeah.
you won't be able to
Actually,
comment on the constant variance.
If it is not homogeneous sigma, it should be, it is uniform. No, otherwise it will be a funnel type.
Correct. But right now, since we are not looking at a residual chart, you cannot comment on the homogeneity at the moment. So this is residual versus index. This is not residual versus fitted value. You can comment on homogeneity when you have residual versus fitted value. I hope you remember that. Yeah. So there's 3 statements, very well said. Firstly is the outlier. Secondly is that, points are scattered around 0 because I expect my errors to be, centered around 0 because the mean is 0, obviously. Thirdly, if you see errors are randomly scattered, you don't see any patterns or, quadratic behavior, upward, downwards movement. They are quite randomly distributed here and there. So all of these
It
3
looks
points.
cyclic also, no?
Sorry.
It looks this cyclic, somewhat of cyclic is there, no?
Fair enough. Yes. Cyclic. Yeah.
Some like a cyclic, it likes going down, coming like that.
Yeah, but then you only have 20 data points.
But if
So
you compared to
yeah.
the upper points, lower
Correct.
points are less, no?
Fair enough. But again, the data point is hardly 20 odd points, right? So I think broad distribution would still remain at 50-50. So shouldn't be a problem. Others, are we good to go with this?
From
Yes,
this
sir.
here also we can find out that the variance is a constant because
No,
it
you
is
cannot find it
uniformly.
by this chart. You will have to get a residual chart for that. That is y hat versus e hat. You won't be able to comment looking at this chart. This is just to understand how errors are scattered, not with respect to the constant variability. Others, are we able to follow?
Sir, how you decide that the y-axis is the mean of the residuals?
That's what the assumption is, right? That error follows normal distribution with mean 0. So I have just added a 0 line over here. So if my mean is 0, I would expect some things to go above and below, right?
No, but how we
Mhm.
come to know that these numbers are mean?
You're saying me, how can you tell that the mean is 0?
No,
Then,
when uh, when we are drawing this plot model versus residuals, you said that these x-axis, sorry, y-axis, we plotted the number.
correct.
Means what is the value y-axis taken? It is the mean or what they?
No, y-axis is the residual. It is the error term. Your x-axis is index. That means residual number 1, residual number 2, residual number 3, residual number 4.
So
Your
at the,
y-axis takes the actual residual value. So for example, I'll help you with this here. So let's say if I add another column in my data set called as residual, and if I just write model dollar residuals, similarly, let's say if I add an initial column of fitted values or fitted values, let's say I add dollar fitted values here, 1 and 2. And if I just show you the data set, so if you remember, So the actual failure time is 0.093, correct? However, my model says it is 0.067. So the delta between the two is 0.025. This 0.025 is something what I have plotted on the chart as the first data point. So this data point, what you see on my screen, this data point is nothing but this number, this guy. The second data point, if you see, is this one. It is this data point. The third number, if you see, it is slightly negative. You see, it's slightly on the negative side. So it is these numbers what I plotted on the y-axis. Since this observation is the first index, it belongs to index number 1, index number 2, so on and so forth. Yeah, Ria, go
Means
ahead.
our upline is parallel to the mean.
It is the mean. It is not parallel to the mean. It is the mean. Because the
Okay.
assumption of linear regression is that your error follows normal distribution with 0 comma sigma square. If you don't remember, then this is nothing but a hardcore statement. You can think of it, right? So if I say it follows normal with mu 0, it means that expectation of E is 0. So my mean should be around 0, right? That's why I plotted the line over here to understand if no numbers are plotted around 0 or not, or if they are scattered around 0 or not.
Okay. For any graph, if we are plotting the upline, means it is the mean.
No. See, AB line or A, so rather call it as AB line, because in AB line, A stands for intercept, B stands for slope, right? Now I don't want an intercept and slope term here. I want to just draw a horizontal line. That is why I've written H. H stands for horizontal. Now, since I know that the mean is 0, I am trying to kind of make a line such that I can see whether data points are around 0 or not. So AB line can work two ways. It can either work horizontally, vertically. You can also give a slope and an intercept term. So if you remember, AB line was something what we studied in QQ plot, to draw a line that passes through the origin,
Yes, sir.
right? The red line is 0, which is mu. Yeah, correct. Absolutely. It is the mu of the error term. So if you say with respect to the error term, then yes, it is the same term. Yes, absolutely right. Good to go, everyone.
Yes,
Okay,
sir.
great. Okay, great. Thank you. Moving on next, an analyst suggests that the 6th row of the original data should be removed. All right. We are coming to part 4a. Let's get to part 4a. Part 4a says, construct a new data set from the original data set with the 6th row removed. Okay, so I want to create a new data set, data.new equals to, I want to remove the 6th row. How do I remove a row from a data set? Go ahead. Anyone?
RM, no?
Sorry?
Remove
RM?
RM. No.
No. Okay. So you use square brackets.
Yeah, square bracket.
Since you want to remove a row, you write the number on the right left hand side. So 6th row is something that I want to remove. But in R, we have studied that whatever number you write down, R will give you that row. So when I write data square bracket 6 comma, R will give me the 6th row. But I don't want the 6th row. I want everything except for the 6th row. Hence you write a negative sign on top of that. So when I write data square bracket -6, it means that except for the 6th row, give me everything else. Simple, good to go, everyone. So when you now run this over here, you see data new have 19 observations. If you just open this one, you see you have 1, 2, 3, 4, 5. See the 6th row is missing, or the 6th index is missing, which helps you understand that the code has successfully worked. Are we clear with 4a, everyone?
Yes, sir.
Yes, sir.
Great. Moving on to 4b. Justify the removal of the 6th row from the original data set. What is the justification?
that is 50, 77. That is a very 18, very extreme abnormal data are there. 50, 77, 61, 88, like that.
Yeah, the justification is that this data point was an outlier. If you
Yes.
see the chart
Yes.
over here, fifth observation was this residual. This observation belongs to the sixth residual, sorry, belongs to the sixth row, right? So since sixth row was an outlier, you are kind of removing it from the data set so that the model can be treated appropriately. Is the justification for 4B clear, everyone? Since it was an outlier, you kind
Yes,
to
sir.
get rid of it. Okay, great. Chalo, thank you. Moving on next, 5A. 5A. Fit the linear model to the new data set constructed in part 4A. Okay, that is very simple. Just get the first code copy pasted here. Instead of data, just write data.new. End of story. Data.new. And also let's give the model name as model.new. Model.new. Simple. Part 5A, very easy, everyone. Free 1 mark.
Yes.
Yes, sir.
Great. Let's move on to part 5B. Comment on the fit of the model from part 5A and compare it with the model in part 1 by comparing suitable statistics from R. Great. What would you compare, guys, here?
That
So they are
R
saying
square.
We
compare
have
model new and compare model what you created right in part 1. R square, okay. Anyone else?
we have to take the summary.
Correct. You will have to take the summary. It says model new or not found. I never executed this. Okay. So guys, again, R square can be taken up here. But again, since you have two regressors, you're working with a multiple linear regression. It's better to kind of look at adjusted R square, right? So if you see the adjusted R square increases from about 48% to 75%. So just by removing that one single outlier, your model performance have substantially improved. See if that is making sense, right?
Yes, sir.
Further, if you see the p-value here, it was it was about 0.15% or 1.556%, which gets even more significant here, right? So after removing that outlier, a global test kind of gets even more significant than before because this p-value is a lot more smaller p-value when compared to this one. Simple, everyone. Are we going too fast?
Yes, sir.
Is everyone able to
No,
follow
sir.
this question? Okay, thanks Ali, thanks Anushka, other people. Okay, okay, thank you everyone. Great, thanks. So that's it then. I think we haven't learned GLM yet. So, this is something what we won't be able to solve or comment upon. So up till part 5B, I think we have discussed the entire question. See if we are comfortable till here, everyone. Guys.
Yes, sir.
So do you want to solve this or should I give you another question to solve? Anything works, whatever you guys are comfortable with. You want to solve this question at your end or should I give you another question?
So we'll solve this.
We'll solve this question. Okay, fair. Not a problem. Great. I will just quickly try to put the entire chunk in your chat box so that you don't have to refer to my screen anymore. Okay. Hold on, I'll just reselect it again. Okay, copied and pasted. Done. So the entire question is on your chat box now. You can just refer to that and keep solving that. Let me know once you guys are done. If we have some more time, we can take another very quick small question and stop for the day. So I'll again move back to my R screen in case you want to refer to anything. I'll just zoom out a little so that you can see a lot of things on the same screen. Sorry. Yeah, I think we have a lot of things on the same page now. That should help you solve quickly. Yep. Everything on one screen now. Great. Cool. Let me know if you guys are having any errors or you want me to discuss any other pointer or anything else with you guys. हाँ मैं हूँ और 15 मिनट तक चलेगा लेक्चर उसके बाद कंचन सर ने बुलाया ना ऊपर हाँ कंप्यूटर टेस्टिंग करना है ना बोल रहे ना आता हूँ लेक्चर के बाद On which sub part are we at the moment, guys? Everyone. Guys, which sub part? 3, 4, 5.
I'm done, sir.
You're done? Okay, great. Thank you. Others? Are we done?
No, no, sir, do it.
Okay, fair. I'll give you a couple of minutes. Someone who's done. Great. I will give you another question to solve. Let me check which question I should give you guys. This is something what we have solved. Let's take a smaller question that you guys can easily work it around. Um, by any chance, do you remember? Okay, I think I can just. By any chance, do you remember the assumptions of linear regression? Matlab, I haven't discussed that. I have plans to discuss that, obviously, but if you don't remember, so do you remember that error follows normal distribution, something like that?
Yeah,
Yes, sir.
errors for a normal distribution, they are linearly related, and Xi's and EI's are YA's and EA's are
Okay.
uncorrelated and all.
Okay, fair. Chalo, great then. I am just pasting up one question in the chat box. So I think since a couple of you guys are done, you can start solving that. Not a problem. Yeah, it's again a 5-marker question. Yeah, I pasted the question in the chat box. You guys can start solving. Yeah. How many of you are yet to solve this question? The rainfall and the cables data set. So Ria is one. Anyone else is solving for that?
Yes, sir.
Okay, okay, fair. Take your time. Let me know once you guys are done. For others who are done, I have already shared one question in the chat box. Start solving for that. Acha, in the meanwhile, are you guys comfortable if we start tomorrow's lecture at 7 a.m. instead of 8?
Yeah, sir, we can.
Okay, so one vote we have yes. Others?
Yes, sir. Will it be from 7 to 11 or?
Nahi, nahi. It
Okay.
will be from 7 to whatever is 9:40. 7 to 9:40. It will not
Yes,
be
sir.
7 to 11. I will forget R if I teach so much of R. So
Okay, sir.
it will be from 7 to 9:40. Okay, great. What about others? Ali, Tom, Kaustubh, Anushka. Does that
It
work?
is very difficult.
Yeah, it's okay.
Sorry, Anushka, what did you tell? Okay, thanks, Ali.
Sir, maybe we can start by 7:30.
7:30. Okay, fair. 7:30 done. We'll start at
And it's-
7:30 and then
yeah.
close by 10 o'clock, approx 10, something like that. Fair enough. Great. Okay, cool. I
Yes.
put it in the chat box also.
Sir, the data set for the second question.
It is an inbuilt data set. So if you just write this term in your R script, it will automatically throw you a pop-up. Right? So I'll quickly solve this question for you guys. You can compare if you kind of had the same solution what I have. So y1 1 data give it lm1 plot lm1 dollar Yeah, so I have the solution on the screen. I am also pasting it in the chat box for your reference. Right. So question 1 again is very simple. It says create a linear regression y1 on x1. So obviously y1 is nothing but your response variable, x1 is nothing but your independent variable. Next it says create a QQ plot and comment on the assumption that the residual follows normal distribution, right? Since they have specifically mentioned standardized residuals, another way what you can do is you can just use a plot function which equals to. So we will learn this. So just what I'm trying to highlight over here is that when you plot the regression model, which equals to gives you a standardized QQ plot as you can see here, right? So one assumption in a linear regression is that error follows normal distribution. So if it follows normal distribution, we have studied using QQ plot that the benchmark line should hold true, correct? So what is your inference? Are your residuals following normal distribution?
No.
Yes, fair enough, because you see there are hardly a few points that are kindly or actually following the benchmark line. Rest,
No.
these points are quite far away. And as you move towards the extreme, there seems to be a couple of outliers. And again, quite a few points deviating. So, doesn't seems like, your residual tends to follow normal distribution. Hence, the assumption kind of does not hold true. See if that makes sense, everyone.
Yes.
Yes, sir.
Great. So in tomorrow's lecture, we will discuss majorly two things. We will discuss assumptions of linear regression, right? Next, we will discuss GLM, right? So this is going to be more theory plus R. This is also going to be a little bit of, not when I say theory, it's just going to be brief recap or an explanation. This is also going to be theory plus R. And thirdly, we will take more exam questions. Fair enough, everyone. These are the three things what I plan for tomorrow's lecture. We start at 7:30 and close by 10:10, not depending upon whatever is the schedule. So that's it then. If you have any question, I just hope the pace is going fine. So I think I don't remember if it was this class. I think you guys told me that you guys did not study GLM or regression in detail or something of that form.
Yes, sir.
So I'm not sure if the pace is going fine or if we're going too fast. So you can let me know now, obviously, or I mean, if there's something that you guys are not able to understand, or if there's something that is going a little too fast, a little too slow, or you want me to spend some time on any other concept that we have already learned, so you can let me know. We can plan accordingly for our future lectures.
Yeah, sir. So we'll look at it today and then we'll ask more.
What about Bootstrap? I did not receive any message that we are facing issues with Bootstrap. So I'm assuming that is good to go.
Bootstrap texture is available on LMS.
It is available.
Yes,
You guys were saying it was not recorded, no? Something like that.
but I checked.
It is
Then
available.
it is there.
Great. Great. Not a problem. So you can take your time before obviously we close for the semester. So if you have anything, you can we can discuss it before we close. So I think another 3 weeks odd we have. So I think by the time of 25th of March, we should be able to close. But again, let's see. Great. So we have about 3 weeks of more time. Try to study everything. Get back if you have any doubts or if you have anything else to be discussed. Otherwise, I think we're good to go for the day. If there's anything else, feel free to let me know now.
The next week we'll go for GLMs and all. Tomorrow.
Yeah. Tomorrow only we'll start with GLMs. Yeah.
Regression is finished.
Sorry.
Regression is over. No?
No. See, GLM is a part of regression only. Linear regression is still, we have just started linear regression. There's a lot of more things for us to study. We did not study interactions. We did not study stepwise backward, forward selection. Nothing is over. It's just the beginning. Anushka, I hope that helps. Yeah.
I thought that it is over.
No, we have just started regression. How can regression get over just in one lecture? We have just started today.
I don't know anything about GLM, so I thought regression is we know a little bit that we thought.
No. We are yet to learn. I'm just starting a couple of things parallelly so that the easier things can be taken first. The more difficult one, I'll bring it a little later on. So that we are comfortable with the easier concepts and then we are able to relate better with the difficult ones or the trickier concepts rather.
Okay.
All right. Great then, guys. Let's stop it for the day. I've already marked the attendance. So yeah, that's it then. See you guys tomorrow, 7:30 a.m. Chalo, bye-bye.
Thank you, sir.
Thank you, sir.
Thank you. Bye-bye.